Okay, so it is our pleasure to have a guest speaker from electrical engineering, computer science, um, and so a Ph.D. student of Dr. Azarderakhsh, Merve Karabulut, will talk to us about Number Theoretic Transform, Python-based speed enhancement. So we're looking forward to hearing the talk. Thank you very much.
You're welcome. May I start? Okay. So my name is Merve. I will be presenting a study for speed enhancement study for number theoretic transform. First, I will talk about my research interests and try to explain what is NTT and what is our proposal on this matter. So cryptography, in a simple way, crypto, it means hidden or secret. It has become key to the digital world security because it ensures that the data we are transmitting or storing is kept private and secure from unintended parties. So to achieve that, we need a cryptographic algorithm that consists of hard match problem, cannot be solved by attackers, and also it should be efficient and standardized. Yeah. So we have different subcategories for cryptography. One of them is symmetric.
Is it this one?
I'm sorry for waiting.
Sure it's working. Fine. There you go. Try it now.
Yeah.
Perfect.
So we have different subcategories for cryptography. One of them is symmetric protocols and asymmetric encryption schemes. For symmetric, we can examine AES or triple DAC. And also we have protocols. Protocols are set of rules and procedures that govern the secure communication between parties, such as SSL, TLS, or SSH. And also we have asymmetric or public key encryption schemes. We can cover RSA or Diffie-Hellman and elliptic curve as well. But after quantum computers, there are new security concerns that have arisen because quantum computers can solve math problem in a constant time. They have very fast computing power. So the currently public key schemes that we are using, RSA, Diffie-Hellman, or elliptic curve, are defeated by quantum computers, according to Shor's algorithm. So we need a better and stronger algorithms that we can use. Kyber is one of them. Kyber is a key encapsulation mechanism. It is resistant to quantum computers. It won NIST's first PQC standard competition. The security is based on hardness of solving learning with error, which is first lattice-based public key encryption schemes. For the digital signature scheme, we have the lithium. It is also resistant to quantum computers. Briefly, I will try to explain what is Kyber, how it's working. So let's say that we have two persons that wants to communicate, Alice and Bob. Bob wants to send a message to Alice. To do that, first Alice needs to generate public and secret key using the key generation and sends the public key to Bob. So Bob, during the encapsulation process, needs to encrypt the message using the public key and generate the cipher and encrypted message and sends to Alice. So during the decapsulation page, Alice needs to decrypt and encrypt the cipher text and verify it. If it's verified, Alice can accept the message request. If it's not equal, Alice can reject the message request. So as I said, Kyber is lattice-based cryptography. So what is lattice-based? Lattice set of points in the space. And we have vectors is a point that can be represented with coordinates. So basis is a collection of vectors. Can produce the points in the lattice. By multiplying or adding, we are producing the points in the space. So lattice-based problem is basically says that, let's say that we have two bases, good basis and bad basis. Bad basis is produced by good basis, multiplying or adding. And the reason that we are calling bad bases is that vectors are much closer to parallel and they can almost cancel each other. They're almost in a line. But good bases are close to the perpendicular. So main problem is that can we find the good bases just knowing bad one? This is our problem. So as I said earlier, lattice base, the first public encryption lattice base is learning with error. It is also Kyber used that. To explain that, I will show this figure. So let's say that we have this polynomial. Let me use the laser. So we have this polynomial and we want to represent that. So we are using a final fit with a modulo of 7 because our highest coefficient is 6. So we want our result to fall in between 1 to q minus 1. So that's why our q or modulo value is 7. And since our highest exponent is 4, we are using n value as a 5. So we are doing the reduction algorithm x to the power 5. So this is our table or array that represent this polynomial. So each row represents the coefficient and number of represent the degree of polynomials. And for each operation, I'm taking modulo of 7 or modulo of q. Are expensive, especially for the hardware. So we need more optimized solution. So we have another method. It is number theoretical transform.
Merve, sorry, we cannot hear, we cannot see your slides anymore, I think.
Okay, let me try. Okay. So
Okay, now it's good. Yes, thanks.
okay. So we have different methods. I mentioned about Schoolbook multiplication, and we have different method, which is called number theoretical transform. So to achieve that, we need to convert our numbers or polynomials to entity domain. Then do the pointwise multiplication, and after that, we are taking the inverse entity to get our final result. As you can see, Schoolbook multiplication has O n square complexity, but for number theoretical transform, we can say that our complexity is O n log n. So which is a highly optimized version. You can see the complexity comparison between Schoolbook and also entity. As you can see, our n increase, the complexity, especially for the Schoolbook, increase exponentially, which is not a good solution, especially for hardware, as I said. So this is the different security levels for Kyber. Kyber has different security levels, and for the parameter set change according to them, it starts with Kyber 512 to Kyber 1024. Our n value is constant. We are taking 256. But as you can see, our security levels get higher. Our failure probability of decryption decrease as well. So this is how entity is used in Kyber. You are seeing key generation and also encryption pseudocodes. As you can see in the line 7020 for each pseudocode, we are using entity domain for our numbers or vectors. So entity is really important for us. This is the pie chart for showing cycle distribution of entity and other operation, especially key generation algorithm. we can say that for sure entity is the second time consuming operation in key encapsulation after key check. Key check is a hash function. It's also used in Kyber. So I would like to talk about how entity works briefly. For convert our polynomial to entity domain, we are using log n layer. So for this example, since we have 8 coefficients, we will be using 3 layers. And each layer has n divided by 2 butterfly operation. Butterfly operation is simple operation. It takes 2 coefficients, and one of the coefficient is multiplied with the Twiddle value, and the other coefficient is not. And adding or subtracting, we are putting in as an input for the other layer. So as I said, the blue circles represent each coefficient for the polynomial, and each orange circles represent the entity. And also Twiddle factor is a complex number that represent the roots of unity. They are calculated based on the modulus and primitive root of the unity. And it should satisfy this equation. So this is how pseudocode for Kyber for entity. As I said earlier, we need to first multiply with the Twiddle factor, then adding or subtracting, we are converting our number to entity domain. So our proposal is that since I know that each butterfly operation are independent from each other, I can execute those butterfly operations in separate cores. Our modern CPUs or current nowadays, our computers has modern CPU structure. It is multi-core, multi-thread structure. And using those separate cores, we can execute butterfly operations separately and increase our optimization. The reason that we use modern CPU, multi-core CPUs, is that some cloud devices also has multi-core structure. And let's say that Alice is some cloud and we want to communicate with each other. And we obtained our result in Intel Core i7 with a speed of 3.2 gigahertz. And our CPU has total of 12 processors. And we exploit parallelism in the CPU using Numba. Numba is Python library. It is for use parallelism. The other reason that we use Python, because application privacy is really important concept in Python. Facial recognition or digital health management or data processing are primarily implemented in Python. The first reason is that it is simple to use, and the other reason is that it has very wide library option. So to achieve parallelism, we need to change control flow because the pass pseudocode requires dependency with the coefficient. So to achieve that, we are creating a vector array that consists of Twiddle factors. Since I know that which coefficient will be multiplied with Twiddle factor and the other is not. So I'm preparing an array that consists of Twiddle factors, and I'm putting one that's it is not going to be multiplied with Twiddle factor. It means no operation, but the other one will be multiplied with the Twiddle factor. This is the preparation for the parallelism. And this is how to initialize our Twiddle array or Twiddle factors array. And I'm putting the half of the size of the array Twiddle values, and the other part will be just 1, which means no operation. Since I prepare my table for the Twiddle factors, now I can change the control flow. I'm putting the Twiddle values multiplication above the for loops that I have recently, and I'm making less operation in nested loop. And I'm taking Twiddle factors from previous table I shown you before. Now I have prepared for parallelism for my code. Now I'm putting Numba. Numba is a high performance compiler to speed up the performance of certain function. It uses just-in-time compilation. I'm setting the parallel to true because I want to Numba to allow the processor to execute parallelly. Now, as you can see, the outside of loop while will be executed in parallel. And also we compared our results with the Python implementation of Crystal Kyber. As I mentioned earlier, it is a PQC finalist, the first post-quantum cryptography standard finalist. And our results makes NTT 120 times faster because it exploits and leverage the parallelism. And our results are obtained on the Intel Core i7 CPU operating with 3.20 gigahertz. This is the performance comparison table of NTT implementation for Kyber and also Numba accelerated NTT. As you can see, our result makes 120 times faster. This is our reference, and thank you for listening. If you have any question, I would like to answer that.
Thank you very much, Merve.
You're welcome.
Any question from the audience or from the wider audience on the internet?
So in the last page of performance comparison, do you compare? So what is the reference implementation for Kyber? Do you compare a multi-core versus a single core performance?
It was single core Python implementation, and we have used multi-core. It is the same computer, but we just add Numba to parallelize, and we compared our result with the base implementation.
But is also the base implementation running in parallel?
No, it
Okay.
doesn't. The normal code mostly implement just one core.
Okay.
But if we want to execute in multi-core, we need to change there are lots of like OpenMP for that, and also Numba makes that. But normally most codes implement or execute in just one core.
I see. Okay. So if you use this library called Number, it automatically use all the cores?
Yeah,
Oh,
it's
okay, I see.
automatically,
Okay.
yeah, execute parallelly.
Okay.
Any other question? Okay. Then, well, thank you very much, Merve, again. So, and we'll see you. We will see next time for another crypto cafe in 2 weeks.
Yeah,
Thank you very much.
Thank you for listening. You're welcome.